So, we have been solving problems of finding electric field and electrostatic potential due to some simple symmetric charge distributions. And along the way, I have given you some ways of performing integrals. What I want to focus today on is calculate. So, today's exercise is going to be calculate the potential and electric field, and that will be left for you. Due to surface charge density sigma phi equals sigma naught cosine phi over an infinitely long cylindrical shell of radius r. So, let us start this problem. So, what I am having is a cylindrical shell of radius r, and phi obviously now denotes the angle from the x axis. So, if I look at it from the top, this is the x axis. The charge density is sigma naught cosine phi. So, it is quite large near the x axis, then becomes less dense as you go away and becomes 0 along the y axis, and then becomes negative on the other side, become again very dense near the negative x axis. This is how the charge density looks. This is similar to what we did in 3D, sigma equals sigma naught cosine of theta in 3D for a spherical shell. And as I have been telling you that cylindrical coordinates become useful when you are dealing with two-dimensional problems. This problem that we are dealing with is essentially a two-dimensional problem, because the third dimension, the z direction, has no meaning. Nothing has nothing depends on z, because the cylindrical shell is infinitely long along the z direction. So, again, if I go by the formula that we did earlier, that is E r equals 1 over 4 pi epsilon 0, and in this case it will be sigma r prime r minus r prime over r minus r prime cubed d, not v prime, but it will be d s prime now, because the integral is going to be over a surface, and I should put a vector sign over the electric field. On the other hand, the potential V r is going to be 1 over 4 pi epsilon 0 integration sigma r prime over r minus r prime ds prime. In our case, the potential or the electric field does not depend on Z. If I were to write the formula for V, that is simpler to calculate, I am going to write V at S, and it will depend on phi, is equal to 1 over 4 pi epsilon 0 integral sigma is sigma naught cosine of phi prime over whatever that r minus r prime is, I will write that, ds prime, and recall that ds prime is now over the cylindrical surface, and this elemental area formula I have already written. So, ds prime in this case is going to be r d phi prime dz prime. R prime is the point which is r phi prime z prime, and r, since it does not, the potential does not depend on z, I can write as, I can even calculate it at phi equals 0. It does not depend on z, and the distance s. Z does not really matter, so I may as well calculate this at z equals 0. It does not really matter. I am sorry, it should not be at phi equals 0, it should be at some phi. So, s, phi and 0, that is where I am calculating it. You can write this formula, do the z integration and all that, and you can calculate things. But I am going to make life a little easier by again what we did earlier, in that I am going to take the cylinder and take a strip at angle phi prime, and I am going to calculate the potential at some distance s and phi due to this strip, and I may as well calculate at z equals 0, it does not really matter, it is infinitely long. So, just by straight formula, I am going to have r minus r prime as equal to integration, square root of s square plus r square plus minus 2 s r cosine of phi minus phi prime. That is the distance of this point at s and phi from this strip. You can easily see it. So, I will do that. Here is this strip at phi prime. I have the point at s and phi, and this is the distance I am calculating. This is mod r minus r prime in this 2-dimensional thing, right. So, this is going to be s s plus nothing really minus r s prime, because r is in s prime direction, modulus, which is going to be s square plus r square minus 2 SR cosine of S dot S prime, which is S square plus r square minus 2 SR cosine of phi minus phi prime. What are S and S prime? Just to recall, this is S and along R is S prime. Okay, so now the potential due to this long strip is going to be V S at some distance S, so let's just write it as R, is going to be lambda over 2 pi epsilon 0 log of R, where R is the distance from this strip with a minus sign. Lambda in this case is charge per unit length, is going to be sigma naught cosine of phi prime times 2 pi R. So, you have this potential due to this strip as minus 2 pi sigma naught R over 2 pi epsilon 0 cosine of phi prime there should be sorry, this is not correct. I am going to correct. I am actually calculating the linear charge only on this strip. So, my lambda is going to be sigma naught cosine of phi prime times r d phi prime, where r d phi prime is the width of this small strip that I have taken. Right. So, I am going to have V due to this is equal to minus sigma naught r cosine phi prime d phi prime over 2 pi epsilon 0 log of square root of s square plus r square minus 2 r s cosine of phi minus phi prime. And therefore, total V at distance s and phi is going to be an integral over this, which I can write this as minus r sigma naught over 2 pi epsilon 0 integral phi prime varies from 0 to 2 pi d phi prime cosine phi prime log of square root of s square plus r square minus 2, that should have been capital R, 2 s r cosine of phi minus phi prime. That is the answer. So, let us just go to the next slide and see what I am getting. I am getting V of s and phi. So, if I take the cylinder, this is the x axis, I am calculating potential at some point distance s, and this angle is phi. So, V of s and phi I have calculated as equal to minus sigma naught r over 2 pi epsilon 0 integral 0 to 2 pi cosine phi prime d phi prime times log of square root of s square plus r square minus 2 s r cosine of phi minus phi prime. This is what I wish to calculate the integral of. I can make my life little easy if I look at this integral in a slightly different way. What I am going to do, just like we did for a spherical case, is take this cylinder and actually consider the point where I am calculating the potential as the x axis, so that the point about which the charge is symmetric or has that cosine phi distribution, so is at an angle phi from this. Let me write this as symmetry axis for charge. And then what I will do is, I will take a point at phi prime on top and a point at minus phi prime at the bottom, calculate the potential due to these two strips. At angle, this angle now is phi equal to 0, all right, at angle phi equal to 0 and add it up. Then I am going to get V at this distance x is equal to, keep in mind that now the charge is given with respect to this red axis. All right. So, the upper strip is going to have a charge, I can write minus sigma naught r over 2 pi epsilon 0 outside. Upper strip is going to have a charge cosine of phi prime plus phi, and the distance, since phi is 0, is going to be log of square root of s square plus r square minus 2 s r cosine phi prime. And for the lower strip, I am going to have plus cosine of phi prime minus phi log of square root of the distance is going to be the same. So, I will just leave it as this. And this whole thing has to be integrated over. Since I am taking phi prime for the upper and the lower both, so the integration will be from 0 to pi. It will cover the entire spherical, the cylindrical surface. So, my answer now, if I add this whole thing up, comes out to be V at x is going to be minus sigma naught r over 2 pi epsilon 0 integration 0 to pi cosine phi prime plus phi and cosine phi prime minus phi give me 2 cosine phi cosine of phi prime, and the log term is common, square root of s square plus r square minus 2 s r cosine phi prime, which by taking 2 inside the log I can write as minus sigma naught r cosine of phi divided by 2 pi epsilon 0 integration 0 to pi d phi prime cosine of phi prime log of square root of s square plus r square minus 2 s r cosine phi prime. Let me see if I am missing r somewhere. When I did the integration over the surface, I should have had an r. No, this is fine. Now, I wrote it in this form because again this is a standard integral which I can look up from the table of integrals, which I told you about earlier, table of integrals, Gretchen and Rizek, and this integral is 4.397 number 6. which is integration 0 to pi log of 1 minus 2 a x cosine, sorry, let me just erase this, 1 minus 2 a cosine of x plus a square times cosine of n x dx is equal to minus pi over n a raised to n for a square less than 1 and is equal to minus pi over n 1 over a raised to n for a square greater than 1. So, this is a standard integral. I have the integration 0 to pi d phi prime cosine phi prime log of s square plus r square minus 2 s r cosine of phi prime, which I can write as 0 to pi d phi prime cosine phi prime log of s square plus integration 0 to pi d phi prime cosine phi prime log of 1 plus r over s square minus 2 r over s cosine phi prime. The first term gives you 0. So, I am left with the integral 0 to pi d phi prime cosine phi prime log of 1 plus r over s square minus 2 r over s cosine phi prime, and compare this with the standard integral from Gresham and Rizek, which I just wrote 0 to pi dx cosine n x log of 1 plus a square minus 2 a cosine of x, which is equal to minus pi over n a raised to n a less than 1, or minus pi over n 1 over a raised to n a square greater than 1. If I compare, I can immediately write that 0 to pi d phi prime cosine phi prime log of 1 plus r over s square minus 2 r over s cosine phi prime is equal to minus pi r over s for r over s less than 1, that is s greater than r, and this is equal to minus pi s over r for r over s greater than 1, that is s less than r. And therefore, the potential that we wanted at s and phi will come out to be, if I look at it from the previous slide, right, go back to the previous slide, look at the formula that we had derived, will come out to be 1 over 2 pi epsilon 0 was there was a sigma naught r there was a cosine of phi there, and now I have times minus pi over s r, so the minus sign here. So, this minus sign goes away and I get, this is for s greater than r. So, this I get as 1 over 2 pi epsilon 0 pi sigma naught r square over s cosine of phi for s greater than r, and I am going to get again I can write this as 1 over 2 pi epsilon 0 pi sigma naught S cosine phi for S less than R. Right. So, I have gotten the formula for the potential. Right. So, what do we have? We have, if I go to the next slide, I have this spherical shell, and inside the potential is S cosine phi. So, it is positive here, becomes less, perpendicular to x axis, and then this was my x equal to 0, and then becomes negative on the other side. And outside it decays as 1 over S. You can also show that the potential V as phi is actually equal to 1 over 2 pi epsilon 0 P dot S over S, where P is dipole moment of the charge distribution. Per unit length. We can calculate that. This is for outside. The shell. We can calculate the dipole moment per unit length. This is going to be sigma cosine phi is the charge times r d phi, and I can multiply by the x distance, which is going to be r cosine phi, and integrate it from 0 to 2 pi. That is the answer for the dipole moment per unit length, and this is going to be in x direction by symmetry. So, P comes out to be sigma 0 r square, this is sigma 0, integration 0 to 2 pi cosine square phi d phi, which is sigma naught r square 1 half 1 plus cos 2 phi d phi 0 to 2 pi, which is pi sigma naught r square. So, I can now summarize this part of the lecture. We calculated the potential V r phi for sigma equals sigma naught cosine phi surface charge density over a cylindrical shell of radius r. Point number 2, like the spherical shell, we could relate the potential outside with dipole moment of the charge distribution. In the next part of the lecture, I am going to now physically interpret this whole derivation that we have done for the spherical shell and the cylindrical shell through Gauss's law. Thank you.